Today we'll do a full whiteboard walkthrough of the PPO algorithm. Let's get started. The reinforcement learning environment that we're going to be using today is called cliff walking, and it's available on the Gymnasium website. This is a very simple environment which will help with our explanation of PPO. In this environment, the goal is to train the agent to navigate a cliff and reach the target. When it reaches the target, the episode ends. Another way to end the episode is by falling off the cliff. If it falls off the cliff, it receives a penalty of -100. Every step that the agent takes incurs a -1 penalty as well. Now you might be wondering, in such a simple environment, why do we even bother using reinforcement learning? We can just eyeball it and know that this is the best path. Or if we were to do it by code, a simple path search algorithm will be able to find the best path. However, there is a flag that we can turn on in this environment to make things harder, and it's called the slippery flag. With the slippery flag on, it adds a factor of randomness to the environment. For example, if the agent wants to move forward, there's only a 33% chance of the environment honoring that move. There's another 33% chance that the agent could slip off to the side. Now with the slippery flag on, this is no longer the best path because there's a 33% chance of falling off every step of the way. Now the best path is no longer the shortest path, but the path that has the highest chance of getting to the goal. Now a path search algorithm would not be able to solve something like this, but reinforcement learning can. For the purpose of explaining PPO, we'll be assuming that slippery is off, and I'm going to compress this map. We retain the same properties as the bigger map, but this makes it much easier to explain PPO on. Let me label the states so we can reference them later. We can use a single integer to represent each state. This can be 1. Okay. There are enhancements applied to PPO to make it run more stable and efficient, but we'll leave those out today and concentrate on the core steps of the algorithm. PPO uses the actor-critic architecture, where the actor performs an action and the critic gives an indication of whether the action was good or bad. The actor adjusts accordingly and the process continues. That's the basic concept. Let's see how it actually works. The actor or actor network is a deep neural network where the input is the state. In this case, with this simple environment, we're using one number to represent the state. For example, our starting state is 7. We'll send that into the network, and we can use one node to represent the state. Of course, other environments could have more than one node if their state representation is more complex. The output is a probability distribution of the actions. Our agent can move in 4 directions, so each node can represent an action. An example of outputs is that there could be 30% chance of selecting up, 25% chance of selecting right, 20% chance of down, and another 25 left. And of course, the sum of the distribution has to add up to 1. Note that the number of hidden layers and the number of nodes within those hidden layers can be adjusted based on the complexity of the problem you're trying to solve. So in step 1 of PPO, we initialize the weights and biases inside our actor network. Another way to call weights and biases is called parameter. So since we're starting with random parameters, obviously our initial outputs are also random and more or less meaningless. As training progresses, the action that leads to more rewards will have its probability increased, while the actions that leads to less rewards will have their probabilities decreased. And if we repeat this process for every state, eventually will lead to the best path. So the actor network actually becomes the brain of the agent. The actor network is also known as a policy network because after training, the agent is going to follow the network like a policy. And it's also known as a model. Let me fill in step 1. Okay, our actor network is still here. I moved our environment up here. Now let's move on to step number 2. In step 2, we initialize the Critic network. And of course, this is the Critic network. The input is the same. It is one node representing the state. The output is a single node, and it is the value. The value is an estimate of the total expected return. So let's say I'm at state 7. The value is going to be -1, -2, -3, -4. Eventually, at the end of training, we expect the value to be approaching -4. This is the best total reward that the agent can get starting from state 7. If it had started from state 6, the estimate at the end of training is going to be -1. It's only one step away from the end of the episode. Of course, when we initialize the Critic network to random weights and biases, the output value is also some random number. Let's say -50. As training progresses, this number becomes more and more accurate. In the subsequent steps, we can see how the value can be used to adjust the probability in the actor network. Before I move on, I want to mention that the Critic network, the hidden layers number of nodes, doesn't have to match the actor network. They are totally independent. In step number 3, we collect a batch of simulations, or we call it trajectories. The size of the batch is a hyperparameter. That means you can configure it to whatever you want. For this example, I'll just collect a batch of 3. For my first trajectory, I'm going to say the agent is going to go to the right. It falls off the cliff and the episode ends, so my action is right. For my second sample, I'm going to say the agent chose to go up and then right, and down. For my third sample, I'm going to say the agent went left. It can't go off the map, so left essentially doesn't do anything. It stays in the same place. After that, it follows the same trajectory as B. Starts off going left, and then the same as B, up, right, and then down. Note that the steps collected in each one of these trajectories should be the same. For example, 128 steps, and they all should be the same fixed size. You can continue the simulation and keep collecting steps until you get to the fixed size. But for this example, I'm gonna ignore the fixed size and just collect steps until the episode ends. This makes the example easier to follow. In the rest of this example, I want to show how PPO decides what the best action is when the agent is in its initial state, state 7. That means we're only concerned with this first step here. Notice that I'm passing state 7 into our network, and I've also changed the random probabilities to nice even numbers so that it's easier to see what changed. Now let's note down what we actually collect. We want to collect our starting state, action taken, the probability of taking that action, but what we actually need in later formulas is the log of this probability. We also need the reward, and we want the value from the Critic network. For trajectory A, we'll collect the experience for this first move. State 7 went to the right, log of 0.25. Remember, I changed the probabilities to all 0.25 and the value to -50. The value -50. The reward is -100 for falling off the cliff. This is the experience for the first step. Now let's quickly do the same thing for B and C. First step is to go up. We're still here, went up, -1 reward. Value is the same state, different action, also -1, -50. Okay, these are the experiences collected for the actions in each one of these trajectories. In step number 4, we calculate the rewards to go. Rewards to go is simply the summation of rewards along these trajectories. The formula looks something like this. The reward of the current time step plus gamma. Gamma is a hyperparameter, usually between 0.9 to 0.99. For this example, we'll just set it to 0.9. Multiplied by the reward of the next step plus gamma square multiplied by the reward of the next step, and so on. This can be written out as a summation formula, but I'll just leave it expanded like this, and we'll use this formula to calculate rewards to go for our trajectories. Let's calculate the rewards and then we'll do some more explanation. Rewards to go of trajectory A. Trajectory A is going to the right, which gets us -100 reward, and that's the end of the episode. So that's all for A. Let me add that here. -100. Let's do B. In B, we go up and then right, and down. So 4 moves. First move is -1. Next move, 0.9 multiplied by -1. Third move, gamma square multiplied by -1. And then the last move, this is about -3.4. Now let's quickly finish up the last one. Trajectory C, we go left and then we repeat what we did in B again. So it's 5 moves, and let me copy the stuff from the top. Here it is. The answer is -4.1. Let me bring these numbers over. -3.4 and -4.1. With the rewards to go, we can easily see which one is the best trajectory, which is the biggest number, -3.4. We'll make use of this number in the next step. Before I go on, let's talk about this formula. With this formula, we want to put more importance on the step that we just took, and then decrease the importance of the reward as the episode goes on. The idea is that the short-term reward is more important than the long-term reward, and that's why the formula is structured like this. But there's also a mathematical reason why we're using gamma to decrease the reward. Imagine an episode where the agent just doesn't get to the target and it's moving around millions of steps. The rewards to go is going to be a gigantic number if we don't have this gamma discount factor. And a mix of tiny numbers and giant numbers is not good for training a neural network. So in a way, the discount factor limits how big the rewards to go can get. You can see that the more steps there are, the smaller the discount factor becomes, which gets to a point where the reward is pretty much negligible. So if you do some calculus and take the limit of this function as the number of time steps reach infinity, the max reward you're going to get is about -10. And that's the significance of having a discount factor. Step 5 is to calculate the advantages. The advantage formula is advantage of state taking a certain action is equal to the Q value of that state taking that action minus the value of that state. Let's do the same as the last step and plug in some numbers and do the calculations, and then we can do some more explanation. Now let's calculate the advantage of trajectory A here. The advantage of state 7 going to the right is equal to the Q state 7 going to the right minus v of state 7. Q is actually just the rewards to go, which is minus 100 minus v. We already have v here, which is negative 50. And this gets us negative 50. Let's do B. In B, we do the advantage of state 7 going up. The Q of state 7 going up is minus 3.4. And also the value is negative 50. And this one is 46.6. Let's finish up C. State 7 going to the left right here. The rewards to go minus 4.1 minus the value is the same, and this is 45.3. These are our three advantages. Now what is actually happening here? We're taking the Q, which is rewards to go, the actuals, minus our current estimate. When the advantage is negative, it means that performing this step going right in state 7 was not a good move. Positive numbers indicates that the move was a good move. In later steps, we'll use the advantage to help us decrease the percentage of taking these bad moves and increase the percentage of taking good moves. We're also going to be training the Critic network, which means the value is going to get better and better. Obviously, we know that B is the best move, so eventually as we train the Critic network, the value is going to become near 3.4. So as the value becomes negative 3.4, we do the same advantage formula. Our advantage is going to get to 0, indicating that this move is not good or bad. We may have found the best move. Now if I repeat the calculation with minus 3.4, this is going to get even worse. Let's say 97. And then the OK move is now a negative number, indicating that it's not as good as the move in trajectory B. Okay, so that is the idea behind the advantage calculation. Let me get rid of these. Let me hop back up to the Critic network and zoom in. Step number 6 is to optimize the Critic network. This is where we send the estimated value into a loss function like mean square error, and then perform back propagation, which adjusts the weights and biases, and our estimate should improve. Now, if none of what I just said made any sense, make sure to go check out my basic neural network video where I solve a 2-node network. Now, the mean square error function, this is what the generic function looks like. In our case, y is our set of rewards to go. We have 3 trajectories, so n is 3. N is 3 here. This y hat here is the estimated value. Basically, we're taking our actual subtracted by the estimate, squaring it, adding all 3 trajectories, and then taking the average. Now, I'm not going to work out this math because the numbers are not very meaningful, but let me explain it this way. I'm going to make a line graph and graph our rewards to go. We had negative 100, negative 4.1, and negative 3.4. These 3 are the rewards to go that we calculated at the bottom. And then we got V minus 50 here. So this is our V. You can see that if we take the average of the 3 rewards to go, these 2 numbers on the right side is definitely going to pull the estimate towards this direction. And we talked about earlier where we decrease the percentage of bad actions occurring and increase the percentage of better actions. That will further diminish the occurrence of the negative 100, which further pulls the number this way. And eventually near the end of the training process, the estimated value should be approaching the best possible action. Okay, so that's how the Critic network improves. Now let me zoom into the actor network. In step 7, we want to optimize the actor network. When we were optimizing the Critic network, we were sending the output of the network into a function like mean square error. When we optimize the actor network, we want to send the output into the PPO clip objective function. And that function looks like this. Now this might look a bit scary, but it's not that bad. Let's break it down. Notice that we're taking the minimum of the left side and the right side. And we see some common pieces on both sides, R on both sides and A on both sides. A is the advantage that we calculated earlier in step number 5. Let's take a look at each side, starting with the left side. R is the probability ratio at a particular time step, and it's a function of the parameters in the network. So R is the probability ratio. Let me do the denominator first. It's the action probability of the old network. What does that mean? The old network refers to the network that we started out with in step number 3. And of course, since we're going through this loop the first time, it's whatever was initialized in step 1. And the action probability is simply the output of the action. So for trajectory 1 going right, it'll be 0.25. Now the numerator, it's the action probability of the current network. So this is gonna look like this. We're keeping a copy of the old probability. Since we're starting to train the network is going to start changing, and current just refers to the current state of the network as we train the network. First time around, it'll be 0.25, and this is simply just 1. So on the left side, we're taking R, multiplying it by A, and let's just put that here for now. Okay, the left side is pretty easy. Now let's look at the right side. Let's see what's happening in this clip function here. So first, epsilon is a hyperparameter. Usually it's set to 0.2. So let's use that for the example. 1 minus 0.2 is 0.8. 1 plus 0.2 is 1.2. And what the clip function is doing, it's limiting R inside this range. When R is less than 0.8, we'll set R to 0.8. When R is greater than 1.2, we'll set R back to 1.2. And if R is between this range, we'll simply return R. And all we're doing is taking that and multiplying it by A. So it's going to look like the same as above, and it's just 1 times A. So we have the left component and the right component. And all we're doing is taking the minimum of the left side versus the right side. And then in the outer layer, the expected value simply means sum up the whole trajectory and take the average. To simplify the example, we're not going to sum it up and take the average. We'll just say we have 1 step. Now let's continue with the example and see what's the point of doing all this. Let me put this on a graph and it will better illustrate what we're trying to do. I'm going to graph RA, which we have on both left and right, and the output L. To make it easier to visualize this graph, we'll just say A is either positive 1 or negative 1. We know that if the advantage is positive, we'll say positive 1. We want to increase the chance of taking this action again. If we were to graph this out, we have R 0.8 and 1.2. Now this is just simply plugging in numbers and getting the output. If we plug in 0, we get 0. If we plug in 0.8, we get 0.8. If we plug in 1.2, we get 1.2. If we plug in anything more than 1.2, we're capped at 1.2. So this becomes a straight line. It's gonna look something like this. What is this saying? This is saying that if my ratio or my current network is only slightly different from my old network, we'll go ahead and make that slight change. As in, we'll go ahead and train the network, making minor changes. But once it gets to a certain point, we don't want to make too big of a change. We're capping it at 120%. Now let's do it for if advantage is negative. When A is negative, we have negative 0.8, negative 1.2. Same thing if we plug in 0, we get 0.8 back. If we plug in 0.8, get 0.8. So we have this straight line here. And then if we plug in anything smaller, we're going to see that it's going to look like this. So basically, this is communicating the same thing. We know it's a bad move, so we want to discourage this move. It's okay to make small discouragements, but let's not discourage it too much. Let's talk about why we're trying to limit how much we change the network in each training iteration. In the early days of the PPO family of policy gradient algorithms, we had reinforce. In reinforce, we don't have clipping, we don't have advantage calculations. All it does was to increase the percentage if it thinks the move was good and decrease the percentage if it thinks the move was bad. Let's say at the beginning of training with reinforce, the batch of trajectories that were collected just so happens to be the longer path. As we do training, because we keep seeing this longer path, we think that this may be the best path. Let's say that we adjusted the percentages and it went up really, really high, 95%. Eventually, we might find the better path, but the percentage of actually taking the better path has gone down to really, really low, let's say 5%. Now it's too late to reverse course. There's just not enough samples to pull the percentages back to the best path. And at the end of training, we settle for the longer path, thinking that that is the solution. This is what PPO is trying to avoid. It's limiting how much the percentages change, so it gives opportunity for the better path to reverse course. This was the reinforce algorithm. Now let's finish up with step 7. When we had the loss function for step 6, what we did with gradient descent was to reduce the loss. But with the PPO clip objective function, what we want to do is to maximize the objective. By maximizing the objective, we'll be able to collect maximum rewards. In other words, we want to do gradient ascent rather than gradient descent. However, libraries like PyTorch and TensorFlow are optimized to do gradient descent. So how can we do gradient ascent in this case? Well, it just so happens that all we need to do is flip the sign of the objective function, and then we can do regular gradient descent to achieve gradient ascent. So that's all we need to finish step 7. Step number 8. Repeat step 6 and 7 again for n number of times. N is a hyperparameter that you can set. So what we're doing is train the critic network again, train the actor network again. When we train the actor network again, this is where our action probability current, our current network, keeps changing here. This is what it's affecting. And finally, in step 9, repeat steps 3 to 8 for t number of time steps. T is something that we define at the beginning, let's say 100,000 time steps or 1,000,000 time steps. We stop training when we hit that number. Each one of these actions count as a time step towards the total number of time steps. Once we hit the total number of time steps, we can stop training. After the cycles of training, we have a better actor network and a better critic network. Going into step 3, we collect a brand new batch of trajectories, calculate the actual rewards, calculate the advantages, optimize the critic network, optimize the actor network, repeat that for n times, and then we do the whole thing again. Oh, but what about the log probability here? Back when we were collecting trajectories, instead of keeping track of the probabilities, the straight wall probabilities, we take the log of the probability. So why are we doing that? Let me hop over to step 7. So it turns out that it's hard to take gradient descent of this ratio here. We can do a little bit of math to transform this equation into something easier to differentiate. Let me do it over here really quickly. So this R is probability current equal probability old. We'll apply log to both sides. In calculus, there is a logarithmic quotient rule that says the top part is the same as taking the log of the numerator subtracted by the log of the denominator. Now let me take the top part back down. We can get rid of the log with exponent. This cancels, and put exponent on the right side. And now this is a easier equation to do gradient descent on. With these two pieces, we can make use of the log probability that we collected in step 3. And there you have it, the complete walkthrough of the PPO algorithm. If you haven't done so, make sure to thumbs up, subscribe, and drop me a comment if you have any questions.